Biodiesel production methods have evolved over the past 30 years from batch types to semi-continuous flow arrangements to true continuous flow schemes. Batch type methods continue to be used and are still very active, especially among smaller plants. Typically, more person-hours are needed per gallon for batch type systems than those for semi or continuous systems, but batch systems are low-cost, flexible, and easy to start up and shut down. One modification of the batch plant uses 2 reactors with 1 or 2 larger settling tanks. This could be described as semi-continuous flow. While one batch is reacting, the second batch is being prepared. When the first one is fully reacted, the contents are pumped into the settling tank, then the next one, alternating between the two until the settling tank is full. Subsequent batches can be placed in a second settling tank. Separation and purification are accomplished during other work cycles. A continuous flow system adapted from the batch process utilizes 2 continuously stirred tank reactors in series, where the reactants are fed in at such a rate that the mixture is homogeneous. As reactants exit the first continuously stirred tank reactor, they have time to settle while the glycerol is drained off, and the upper phase is fed into the second continuously stirred tank reactor along with fresh reactants so that the reaction is complete by the time the product exits the second reaction step. Plug flow systems are set up to feed reactants at optimal rates and to push the mixture through pipes containing a series of static mixers. Some schemes make use of dynamic ultra-high shear mixers to speed up the reaction by mashing the reactants together by shear force and the action of cavitation. Ultrasonic units have a similar effect to high shear mixers, but have no moving parts and are credited with super fast reaction times at high flow rates. The supercritical method relies on very high temperatures and pressures in the range of 350 degrees C and 1200 psi. Under these conditions, reactions happen quickly without the aid of a catalyst. Glycolysis involves combining the feedstock with glycerol and methanol at high temperatures to convert the FFAs into mono and diglycerides. This reaction, which yields pure water-free glycerides, is followed by a conventional base-catalyzed transesterification step. After separation, the glycerol is purified to be reused in glycolysis, while the esters are typically distilled to produce a high-quality biodiesel. Another method for utilizing high FFA material is to convert the FFAs to esters using an acid catalyst. This esterification step can be used with feedstocks with FFA content ranging from 2 to 100%, but is typically applied to oils and fats at the higher side of that range. This process can be followed by transesterification to complete the reaction. Researchers at the U of I have been looking at in-situ transesterification of lipids and microalgae in sub- and supercritical methanol. In this high-temperature, high-pressure process, the FFAs and triglycerides are converted to biodiesel as they are being extracted from the biomass. Learn more at biodeaseleducation.org.